today's chemistry session. Today, let's see one question. You can see here, it's a frequently asked question. Using VBT, explain the geometry of CONH3 6 times 3 plus. Or that same question is asked in another format. For CONH3 6 times 3 plus, describe the type of hybridization, shape and magnetic property. The same question is asked. Write hybridization and shape of CONH3 6 times 3 plus. So it's the same question asked in different ways. Let's see how we can use VBT to explain the hybridization, geometry and magnetic behavior of this particular coordination compound. The given coordination compound is CONH3 6 times 3 plus. First thing is to know its atomic number. So cobalt is having atomic number 27. So we can write its electronic configuration argon 3d7 4s2. Next step is to know the oxidation state of central metal ion or cobalt. So its oxidation state is 3 plus. You can easily find it out. Amine ligand is neutral and so it will have a 3 plus charge. So once we know the oxidation state, let's write its electronic configuration. CO3 plus will have the electronic configuration argon 3d6 because 3 electrons are lost from that particular atom to form CO3 plus ion. Now let's consider its outer electronic configuration of CO3 plus ion. So CO3 plus ion will have in its outer electronic configuration 3d orbitals, 4s orbital and 4p orbitals. So the electrons will be arranged in its 3d orbital according to Hund's rule of maximum multiplicity. 6 electrons are there. 1, 2, 3, 4, 5 and 6. These are the 6 electrons in the outermost orbitals of CO3 plus ion in the outermost 3d orbitals. Now, next step is the formation of coordinate covalent bonds with and central metal ion and the ligands, approaching ligands. Now here what is important is what type of ligand is approaching the central metal ion. The ligand that is approaching the central metal ion is amine ligand. As we have discussed in the earlier session, I have introduced a few examples of strong ligands. So amine comes in that category. It is a strong field ligand. Amine is a strong field ligand. So what will happen is this strong field ligand amine, when it approaches the central metal ion for the formation of coordinate covalent bond, it will push these unpaired electrons of central metal ion in the 3d orbitals to get paired up. And so they get paired up. Let's see the formation of CONH3 6 times 3 plus. Let's see. This is the 3d orbital. In that, all these unpaired electrons are coupled. These two will get paired up and these two will get paired up. They are coupled to get paired up. And now we have these empty orbitals here available for the amine ligands to take its place. 4p, 4s, 3d. This is the 3d orbital. For 6 amine ligands are approaching. They are making coordinate covalent bond with the central metal atom. So each ligand will donate a pair of electrons. That is the formation of coordinate covalent bond. You have already learned. And so this is the first pair. There are free orbitals they can occupy. And then this is the second pair, third pair, fourth pair, fifth pair and the sixth pair. So all these 6 amine ligands have made or taken place in the orbitals of central metal ion and thus forming equal number of hybridized orbitals. New hybrid orbitals are formed. So we can know its hybridization very easily. How would you find out? 2d orbitals are involved in hybridization here. This 1, 2. 2d orbitals. I mean 2d orbitals of the 3d orbital. So 2d orbitals are involved. One s orbital is involved. So S is written here. And how many p orbitals are involved? 3. 1, 2, 3. So 3 p orbitals are involved. So this is the hybridization. So D2sp3 hybridization. The formation of by the formation of CONH3 6 times bond has got the hybridization D2sp3. So once you know its hybridization, you can easily predict its geometry. We have already learned how to predict it. Once this hybridization is D2sp3, its expected geometry is octahedral. So octahedral geometry. It is in octahedral geometry. And then what is next? We have to know whether it is an inner orbital complex or if it is an outer orbital complex. We have already told if it is n-1 d ns np, it is an inner orbital complex. We can see here. Here n is 4. So ns is 4 is here. np is 4p here. And then d is 4 minus 1, 3d here. 3d, 4 is 4p. These are the orbitals involved in hybridization. So this is 3d. So this is in the form of n-1 d ns np. So it is an inner orbital complex. This compound is an inner orbital complex. And all these electrons are paired up. It is an inner orbital complex or low spin complex, anyway you can say. And then whether it is paramagnetic or diamagnetic. And you can see here, since all the electrons are paired up, no unpaired electrons are present, and so it is diamagnetic in nature. So that's all about this particular complex. You have to know, and if you are writing all these points, you will get full mark for that particular question. So this is all about today's explanation about VBT theory. We will see in the next class.